For the second exercise, we are asked to write a string equals function, which returns 1 if strings are equal and 0 if they are not. So a typical data type when we pass strings in C, data type is going to be a const char star, which contains a pointer to the first character of a string. And this const denotes the fact that we cannot write to this string. So it's a pointer to a constant char. And a constant char is a char that cannot be modified. Typically, strings are stored in read-only sections of memory. That's why you cannot modify them. That aside, P1 and P2 stores the address of the first character of strings. Both of them, the address of a first character of a string. Remember, strings are stored in memory, whereby each character takes in 1 byte of this memory, starting at a certain address, and then the string's length is determined by where the first null byte occurs. So if you have a string of 5 characters, you will find 5 bytes of ASCII characters, and then you will find a null byte. Great, that's the representation of a string. And let's see how this function compares these two strings. So what it does is it checks if the P1 dereferenced, so the first character of the P1 string equals the first character of the P2 string in the first iteration. So because P1 is still pointing at this point to the first characters, and P2 as well. If they are not equal, well, then we are already done. The first characters of two strings are not equal. Of course, the strings are not equal. But let's say they are equal. We found two strings with the same first letter. Well, what then do we need to do? In that case, we need to check, did we reach the end of the string? So, did we just read the null byte in both strings? That means both strings were just ended. Maybe it were both empty strings, for example. Well, in that case, if we reach the null byte, that means we're done. And we say, yes, this matched. If not, we simply have to advance our pointers to point now to the next string characters. So we advance P1 and P2 to point to the next character in the string. And then we do the same comparison again. Do the second characters match? If ever we encounter non-matching characters, we return 0. If ever we return or encounter the null byte, that means all characters matched and both strings were ended. That means they are exactly the same and we return 1. Let's implement this function in RISC-V. So we wrote two strings, which are obviously the same. We load the addresses in A0 and A1, calling conventions. We jump to the string equal function. And this is important, we load a byte, not a word. If you're going to load a word, then you're going to load 4 characters at once. Which, even if those 4 characters at once don't match, but yeah, then you could say, yes, we advance. And if they do match, you could do it 4 characters at a time and then switch to load byte whenever they don't match. But you're going to run into different problems as well. So if you thought about that, like let's compare multiple characters at the same time, it's possible, but you're going to encounter different issues. Let me quickly explain those first, because you might run into those in the future. And in the next section, you will also learn how to deal with them. So when I write ABCDE, or just ABCD, in fact, is fine. These two strings, let's first see what happens when I assemble my program. I'll get back to the RISC-V code in a second. When I assemble this program, these strings are placed into memory. How is this done? Well, so bytes in a word are stored in little endian order. What does it mean? When we read a word, these are all words in our memory, you read them, the bytes in those words, from right to left. What do we mean? Well, at this address, 1001 and 4 zeros, if we load the byte at that address, well, It's going to be a byte out of these 4 bytes that you see here. But which one? Well, the rightmost bytes. And if you load 1 byte next byte, that's the 62, and then the 63, and then the 64. So we read these bytes from right to left. This is a little endian order. This is very standard. Has to do with low-level optimizations. You can look up if you want to know more about little endian byte order, but that's what's happening here. So now we can read our string. So it was A, B, C, D. 61 is A, 62 is B, 63 is C, 64 is D. And then the next byte in memory is this null byte. And then we go again. A, B, C, D. Now, this second string starts at the offset, well, or the address 10010005, right? This null byte is at 4, and at 5 you have the 61 byte. That means this string is not stored at a location which is a multiple of the value 4. And we might have explained this in the past, but I don't think so. LW only works with addresses that are multiples of 4. That's called word alignment. So all of the addresses you see here, those are multiples of 4. And those words you can load. But you cannot write an LW instruction that reads these 2 bytes and also these 2 bytes. This has to do also with processor implementations which need to be efficient. So it's not allowed to load an address which is not a multiple of 4. So if you would try to use LW here, you would need to make sure also that your strings are not are word aligned. Enough about that, this is a problem we actually encountered with some students in the exercise session, so that's why I wanted to quickly address this. In the next session about operating systems, you're going to learn how to deal with these misaligned loads, for example, because these cause an exception and cause your program to stop. Alright, so back to our code. We loaded the addresses of both strings and we jumped to string equal. We loaded the bytes at these addresses in T0 and T1. So T0, T1 both contain the first letters of A and B respectively. Since A0 and A1 contain the address, then either they match or they don't. In this case we say if they match we're going to loop, and if they didn't match then we're just going to return 0. That's this part, return 0 if they don't match. Of course you can write this the other way around. You could write branch not equal and then return and write the loop here. Same thing, doesn't matter. So we write a loop here, and here we are going to branch if T0 equals 0. What does that mean? If the first character or the current character of the string was equal to the null byte. So this is another thing I have to explain, which is not explicitly said in the exercise. But so first of all, if you use single quotes in C, you're defining a single character. And how is a character stored in memory? Well, with its ASCII representation. So you can look up an ASCII table and it will say the value A, the small letter A, has an hexadecimal value of 61 and so forth. Now the null byte has an ASCII value of 0. This is the textual representation of the null byte, but what this actually will do is it will compare what's stored in P1. Well, this is an address, it will follow the address and it will compare that to 0. This is simply a comparison to 0. You could have written the number 0 here and it would have worked exactly the same. So that's what we do here. We check if T0 was the value 0, if it was the null byte. If so, we are done and we return. We already explained how that works here. That means P2 is also null byte and all characters match. So we have an equal string, we return 1. If this is not equal, well then we need to check the next character of the string. So we add 1 to both addresses. And this is the point of the second exercise as well. We're writing ++ behind the pointer. Previous previously we incremented our pointer by 4, but now, since we have a pointer to a char, we increment our pointer by 1. Size of the data type is just 1 and not 4. And then we jump to our loop, which is the beginning of the string equals function. So that's how we implemented the second exercise.